Bom, bom dia a todo mundo, a todos. Vamos começar a palestra do professor Edouard Ivanjko, da Croácia. So, good morning, everybody. My name is Professor André Luiz Cunha from Department of Transportation Engineer in São Carlos School of Engineer. We are here with the Erasmus program. Last year I was in Croatia with Professor Eduardo, and I have 1 week for teaching and some advisor with his students. And now Professor is come to Brazil for the same program. And today he will teach us, presenting a lecture about reinforcement learning and traffic control. So welcome to Brazil, Professor Eduardo, and take your time.
Thank you, Professor André, for your kind introduction. And for the starter, I want to say to you all, Dobar dan, bonjour, and hello, thank you for coming to listen to my lecture. And today I will talk about reinforcement learning and how we can apply it to traffic control. So I see a bunch of new faces also in the city there in Sao Paulo, and I'll just then briefly say again about my origins. So I am coming from the Republic of Croatia. That's a part of the European Union, and you can see here is Europe, and here somewhere in the middle this little dark green country, that's Croatia. We are not a big country, slightly less than Brazil regarding our area and our number of inhabitants, but when you want to go for a nice tourist country and see some nice islands, then Croatia is the place to be. Our capital city is Zagreb. Here you can see the square on St. Marko with our building of the parliament, and of course the church of St. Marko with the historic roof in colors presenting all of our emblems that we had to our history. Maybe you've heard about Croatia because in the beautiful city of Dubrovnik, you can see him here. The movies Star Wars and the series Game of Thrones has been filmed, including the cities of Zadar and Šibenik. And of course, maybe you've heard about our company Rimac Automobili or Rimac Cars that is currently proudly producing the fastest electrical car in the world. And if you have some millions of dollars of euros to spend, you can buy such a car and drive around. And some other interesting thing about my country, about our industry, we have the company Concher, and this company holds a few % of the world production of various transformers. Not mass production, but specialized transformers. And if you look at the number of inhabitants that we have, that's a quite big chunk of the market. I come from the University of Zagreb, and it was formed in the 17th century by Jesuits, and now it has 29 faculties, 3 academias, and we have over 5,000 research staff members and over 50,000 students currently. My origin faculty is the Faculty of Transport and Traffic Sciences. We are rather a young faculty, formed in 1984, and now we are currently have 15 departments that cover all transport modes, meaning road, rail, air, water, and water is only related to inland waterways, and our faculties at the sea cover then the sea traffic. We have also a department for logistics, for intelligent transportation systems, and we also have a branch of aeronautics because we teach civil and military pilots. Currently we have somewhat about 100 research staff members and over 2,000 students, and my faculty publishes also the journal called Promet, and that's the Croatian word for traffic, so Promet, Traffic and Transportation, and is cited in the most important databases for research. And as you can see, it is also an impact factor, and if you want to publish, let's say, some beginning results of your PhD research, using this journal is one way to do it. I'm working in a department of intelligent transportation systems, and the head of the department is Professor Satko Mandžuka. We are a rather small department consisting of 6 professors, 1 postdoc, 5 young researchers and 2 lecturers. And we also have 2 chairs, the chair of applied computing, and I'm a member of this chair, and it's led by Professor Tonči Carić. And the other chair is about transport telematics, led by Professor Pero Škorput. So my research interests are, of course, related to intelligent transport systems, and I'm into road traffic control, and currently me and my young researchers try to apply machine learning techniques to improve the traffic control. And some of the results that we have achieved I will also present today. And for this, of course, we are into modeling and simulation of road traffic, and to use good control, we need some system to forecast the traffic parameters. And one of the ideas is also to include autonomous vehicles in the simulation to see how we can act on the transport network. And also, we had a project about how to apply computer vision in road traffic. My email contact and personal web page are here, and I also brought some business cards, so after the lecture, do not hesitate to come here, ask something, or take the business card, so you can send me an email later. I'm also a member of the Scientific Center of Excellence for Data Science and Cooperative Systems, and in scope of this Scientific Center of Excellence, we have the project DataCross, where we received some funding to solve problems related to data science and cooperative systems and apply them into traffic control. Now, coming to my lecture, and during my lecture, I know that English isn't your, let's say, native language. It's also my number 2. So if you don't understand something, do not hesitate to raise your hand so we can explain it in another way, discuss a little bit, and try to transfer the knowledge. The outline of my presentation will be as follows. So I will be giving first a little bit of an introduction, and after that I will be talking about agents. And here I have to disappoint you a little bit, because I will not talk about James Bond and all of the adventures that he had, but I will talk about some computer structure programs that can act as agent. After that, I will give the basis of reinforcement learning, and following by basics of state approximation, and I will mention 2 examples how to apply reinforcement learning to variable speed limit control as, let's say, a more complicated one, and a simple implementation to ramp metering. And after that, I will end with a summary, and after that we can take to discussion and answer all of your questions. Now, when we look at some general approaches to control, we always have some process that has some inputs and has, of course, always an output value. If we look at, let's say, a motorway, then we have the mainstream where the vehicles are going, we have the on-ramps where the vehicle can enter the motorway, and of course we have some possibilities, some control inputs to change the state of the motorway, and of course some noise regarding to the weather condition, and of course if we have many cars at the motorway, we will have congestion. If we can measure some output values, including a measurement system, so we use some sensor and process the data from the sensors, we can compare the state, the output value of our controlled process, with some reference value or some desired state that we want to achieve. If the desired state equals to the current state of our process, then everything is okay and we can relax. But regarding traffic, in rush hours, we have, let's say, a large difference between the state that we want to have in our network and the actual state. So we compare these 2 values, and regarding this difference, meaning that is some control error, we can apply some control algorithm to compute an action that we want to apply at the process using some actuators. So in an urban motorway, we can apply some variable speed limit on variable message signs, and of course we can apply ramp metering and to stop the vehicles from entering the motorway. And these are then the actuators. And in order to design a control algorithm, or more generally speaking, a controller, then we have to solve many problems. The first problem that we have to solve, that we have to produce a model of our controlled process. So it has to be known. And if you want to make a good controller, then model accuracy is crucial. After that, we have to define some performance measure so we can evaluate the quality of our control to see if we have a good output value. And of course, the designing controller has to be stable, meaning if you're looking at traffic control, we don't want that our controller causes congestion. So that would be an instability. And generally speaking, if we have a bounded input value to our process, then we want to achieve a bounded output value so everything is stable. And at the end, we have also a large problem related to robustness, meaning that if you have some changes in the process parameters, and if you look at our transport network, when the rain is falling, then we have a big change. The traffic slows down and automatically we have congestion. So we want to have robustness to such changes so that such changes do not affect control quality significantly. There will always be some influence, but we don't want to have some significant changes. And looking into the details, let's say, of characteristic of a road traffic process, then we can say it's non-linear. So maybe in some cases small changes can cause some small changes of input traffic can change a lot the state of the transport network. The process is stochastic, meaning that we cannot predict it exactly. So we know approximately how the traffic will be behaving each day regarding the rush hours, but if some parameter change, then we have big differences. Then we have a process that's time variant, so the users don't use the transport network always the same time. So in the morning, we are all getting into our cities and have some travel patterns, and they are not as equal as the travel patterns in the afternoon, during the night, etc. And then we have so-called distributed parameters, meaning that quality of a road is not the same on the whole length of the road, or if you measure the traffic parameters like flow, speed and density, then they are also change regarding of the distance from a starting point. And at the end, that's very problematic in urban road network. Then we have the situation that network segments have significant interactions. So if you look here at the piece of our road network in the city of Zagreb, we can see here is our main street Ilica, and during rush hours it's very congested. So this red-orange color denotes some queues in the Google map, and we can see here that a problem that is existing at this intersection spills back and closes some previous road here, meaning that there is significant interaction. And as, let's say, a consequence, we have that fact that the road traffic network is difficult to model. When we look into the modeling of the traffic network, then you can say, okay, but we know the geometry. So I can look in a map, I can see the configuration of the streets, the number of lanes, etc. Yes, that's available. I can measure traffic flows and vehicle speeds, okay, and use this as an input to my model, and then I have to calibrate my simulation model to be exact. But if we have some different driver behavior or different road condition, then that results in different states dynamics of the network, meaning that we have to take into account many parameters. So we have to measure what's happening when it's raining, when it's fog, when it's hot, etc., and produce, of course, many models. And then, of course, when we have such different process models, we need to adapt our controller. Another thing that is problematic, that today we want to manage big urban traffic networks, meaning not just one intersection or let's say green wave of several intersections, but we want to look at the whole network of a city, or a city including its surrounding roads regarding, let's say, urban motorways that connect parts of the city. So for this, we have then many intersections that has to be controlled, and for each intersection, we have a different signal programs that is being executed during the day. And regarding the city of Zagreb, we have in Zagreb somewhere about 450 intersections. And to build a model of Zagreb, it's not so simple. So I don't know if anybody knows the number of intersections here in São Carlos. Is it larger or smaller than in Zagreb? And maybe in Sao Paulo? Is the number smaller? So you can imagine that we have a big problem. And going further, except of the signal programs, we can always use driver information systems to tell something to the drivers how they should behave using various variable message signs. And some of them used today can present a part of the network and give information which directions are congested, which are free, so you can change your behavior. And of course on urban motorways, and that would be then the topic that I have been watching today. Except of the signal programs, we can always use driver information system. Okay. So that was not a question, just okay, just noise. So we can filter that out. Continuing, so I will concentrate today on urban motorways, and on then we can use ramp metering. Using simple traffic lights, we can stop the vehicles from entering the mainstream, and then if we have lots of vehicles on the mainstream, we can prevent congestion happening and, let's say, prolong the pre-phase of congestion. And using variable speed limit control, we can help the system ramp metering in solving the congestion problem, and of course increase the safety on our motorways. Looking into this example of Croatian motorways, so we have a bridge in our area Lika that has many mountains and fog, and in the winter it is crucial to inform the driver if there are any problems here, so they can reduce the speed and not run into some foggy or icy conditions that are dangerous. One possibility that we have at hand today to solve the problem of controlling such large and complicated system is to apply methods from the area of artificial intelligence. And with the development of artificial intelligence, first the controllers were taught offline, meaning in the first phase, people defined fuzzy logic and fuzzy logic systems that can be applied in control, and such systems needs many rules. They are in the form of if-then rules. So if some conditions are fulfilled, then I have to do some action. For this, expert knowledge from, in this case, traffic experts can be used to define the basic rules as a baseline, and after that, for such complex system, they have to be optimized and then they can be used. Better way is to use neural networks. So if we collect some data, meaning some measured traffic parameters and some good solutions to the traffic problem from existing, let's say, signal programs, so then we can create some input-output pairs and learn a control law to the neural network, since the neural network is a universal approximator. And of course here we have the problem that the control quality depends upon the learning data set. So if we have better data for learning, then we have a better control. And if you look at this, let's say, approach, then of course if we teach something offline, then we have some parameters, and when we apply them and some change happen in the system that we want to control, then we cannot include the knowledge into the system. And that's not good, because everything is changing. So a better way to do is not to teach the controller offline, but to teach the controller during operation. So, in this case, the controller is an agent, and again, disappointing you, it's not James Bond and many adventures, but just a piece of software and hardware, of course, that interacts with its environment. And in this interaction, the agent can evaluate if he did something good, and for this he receives positive rewards. And in the other case, when he did something bad, he receives a negative reward or punishment. And this is the basic concept of reinforcement learning, to see what actions are good and what actions are not so good. And now to come further to define our agents. And in the sense of control or computer science, we can say that an agent is anything, a piece of software or hardware, that we can look at something that is perceiving its environment using some sensor measurements, and after that it uses its actuators to act upon that environment to change its states. So as we can see in this figure, we have an agent, and that's the environment in which the agent operates. He has some perception, meaning sensors that are measuring the state of the environment, and using his, let's say, knowledge, agenda, goal, control law, he acts with his actuators on the environment. And regarding agents, we can include today also the learning capability. And this is very important when we look at our humans. We are constantly, let's say, improving ourselves. And if we define us humans as, let's say, an agent, then we can say we have sensors as an agent. So we have eyes, ears, etc. to measure the state of the environment. And let's say using your ears now, you can listen to me and process my information. And if you have a question, then you can use the actuators, let's say your hand and your mouth, to say something, and then we can start a discussion. And of course, in our heads, we have our brains, and our brains have the ability to process the information from the surroundings and to constantly learn when we are in our environment. And during every second of our lives, we humans learn something new and process it. When we compare our humans to, let's say, robots, then robots have also sensors, artificial ones like cameras, gyros, etc. And also they have some actuators, and in most cases that are various motors that move the parts of the robot. And if we look at robots, generally most of the robots don't have the learning capability, and they just execute, let's say, the knowledge that has been given by the programmer, and they execute the same motion during the whole day. Regarding agents, for control, we want to use so-called rational agents, and rational agents select for each possible, let's say, state, an action or a sequence of actions to reach a goal, and in a matter that the performance index that is built in the agent will be maximized. So we want always to obtain some best possible decision to reach our goal. And regarding a performance measure, that's an objective criterion for success of the agent's behavior. And of course, if you want to achieve some goal, you want to do it in a minimal number of steps, actions, etc. And of course, we want to use so-called autonomous agents, where the behavior of the agent is determined not by some input from an operator, but his own experience, meaning that he has learned some knowledge, and then during operation he can apply and adapt that knowledge to the changes in its environment. just as we humans. If there is, let's say, a rain outside, we will all use an umbrella and go under a roof. And that is using our knowledge and adapting ourselves to the changes in our environment. To specify the most important settings to design an agent, the so-called peace concept is used. And the peace concept has then a performance measure to evaluate how good is an agent performing. Then we have an environment. We have the actuators of the agent. And of course, we have the sensors of the agent. And if you look at this scheme here, that means that an agent, as we said, operates in some kind of environment. And he can measure, using sensors, the state of that environment. And using its actuators, he can change the state of the environment. And for his action, he will receive reward using its performance measure. If we look as an example, we can take, let's say, a taxi driver. And we know today that some companies in different areas in the world are testing autonomous taxi vehicles. And regarding the performance measure for a taxi driver, we know that every company wants that the taxi driver drives safely to return the car in the evening in one piece, not in many pieces, so that the trip that he makes, well, fast, but according to the traffic regulation, that the customers are happy and comfortable, and of course to maximize profits. The taxi driver isn't here for us, it's there to earn money, of course. The environment regarding our, let's say, taxi driver are the roads on which the vehicle is driving upon, and of course other traffic, pedestrians and customers. We know every taxi driver has to be polite. The actuators that are here for our taxi driver are, of course, the actuators in a classic car, meaning we have a steering wheel, we have our light signalization, brakes, etc. And of course, the sensors, when the taxi driver is a human, then he has his eyes, ears, etc. But if we have an agent, meaning a computer system, then such system use cameras, sonars, laser rangefinder, GPS, etc. to measure the state of the environment and, of course, where the taxi is in its environment. And if you look at the development of agents, we can define different types of agents. And first agents were so-called simple reactive agents. And those agents just reacted to the state of its environment. So when the state changes, the agent can measure it, and using some rules in his database, he can decide what to do according to the changes of his environment. More, let's say, advanced agents use then a model-based approach, meaning that they have not rules for behavior, but the model of their environment, meaning that if they don't have, let's say, knowledge how to react in some situations, then maybe the model can make some generalization of the new states of the environment, so the agent can react better. After that, we had so-called goal-based agents, and they are very useful in the case when we cannot achieve a goal only with one action, or let's say a few actions, but we have to act in a good manner in a longer sequence of actions. Then when we have a long-term goal, such agents can perform better. After that, we have so-called utility-based agents, and such agents, when they decide what they want to do, they are using prediction model to estimate what the chosen action will do. And if the prediction is good, then they apply that action. And if the prediction is not so good, they try to change the action and then perform better. And these mentioned types of agents don't have the learning ability, meaning when we program them, set them up, they're using just the current settings to work during the whole time. And our idea today is, when everything is changing and very complex in our environment, especially, let's say, in our transport network, we want to use so-called learning-based agents. And this block scheme presents such a concept of a learning-based agent. It contains also the basics of a so-called reactive agent. So we have here our environments, the sensors, and a performance element that can decide what to do, what actuators have to act upon the environment. So this is the simple reactive part. But this other part uses sensor measurements and the performance standard or the performance function to do some criticism, to evaluate if the agent is behaving properly, good, and give some feedback to the learning element. And if the learning element detects that in some parts the agent isn't performing good, he can create so-called learning goals, and our problem generator can choose some different action to a little bit act on the environment to begin the process of learning. And regarding the learning element can then change the current knowledge in the performance element, and during time, if everything is set up correctly, then our agent can perform better. And to, let's say, improve the knowledge of our agent, we can use so-called reinforcement learning. And reinforcement learning can be defined as an approach for programming agents by using reward, positive reward for good action, and negative reward of punishment for bad action, and without needing to specify how the agent has to achieve some task. So we just tell the agent, this is good, this is bad, upon his performed actions, but we do not explain how he has to achieve the goal. And how to achieve the goal of the agent is then learned during the teaching process, during his operation. And the goal of the learning process, as we can see here, is to find some control policy, or we can say a control law, that we will maximize all of the rewards that the agent receives during his lifetimes. So in every, let's say, time step when he acts upon the environment, to choose the best possible action. So our agent, when he does an action on our environment to change the state of the environment, he perceives what was happened, and also he receives a reward, and using this reward he can also change his so-called learning fidelity, how to get into, let's say, states that he hasn't observed yet, to improve his knowledge, how to control the underlying process. And regarding the basic steps of reinforcement learning, we can define them as the first one, to observe the current state, let's say state in moment t, and using that value about the current state, we can decide which action we can use in this moment to change the state of our environment, let's say to reduce the queue length on our intersection. After we decide what action is the best, we can perform that action and then wait a little bit to see what happens in the world when the environment reaches its new state in the moment t plus 1. And when we have the new states, we can then observe if the new state is better or not so good regarding the past state, and we can compute an reward in time step t plus 1, because we have to wait what the action will do to the environment. And regarding this reward, we can apply some learning procedure from this newly gained experience. And of course, when we are done with this, we just have to repeat this a few times, and after some time we will have a good controller. Regarding the motivation for applying reinforcement learning is that in this case we only have to define the goal, what the agent has to do, and not to define how that the agent has to achieve that goal. So in the beginning, the agent just knows his reward function, but he doesn't know how to get good grades from his reward function. And during the process of learning, he should, in some kind, get answers how to optimally achieve a goal. And then using reinforcement learning, we can find better final solutions, because if we measure the state using several variables, we can see in those variables, let's say, some complex interaction between parts of the traffic network and have a better agent experience. And of course, the good thing then when we create an agent and also we have some assumptions about the process, then if we do not had made some assumptions, that isn't a problem for the agent. And of course, the last thing, we humans do not like to work hard every day, and it is better to let the computer do the work to obtain a good solution. And that's, in this case, very good, because even when the operator in a traffic control system doesn't change some settings, the agent can learn and the agent doesn't go to sleep. To achieve this, we have to look a little bit into the mathematic background. And for applying agent, crucial thing is to see how the decision process is working. And for this, we can define a so-called Markov decision process, or MDP. And during every decision process, we know that if we want to reach a final decision, in this case that would be our goal, we have to make multiple decisions, or multiple actions have to be performed to reach the goal. For just a simple example, when we want to go to our working place or studying place every day, do we have to make only one decision? Or only one action? We have to make a lot of decisions, a lot of actions, just to get up, to dress, to drink something, etc., etc. And all of these are some decisions and actions. And of course, each decision or each action that we do affects the decisions and actions in the future. So we are changing our states, and we can denote every state with a notation, and regarding some starting state and the ending state that we want to achieve, we have different possibilities. And when we change a state, then when we have different possibilities, then for every transition between two states, we can have, let's say, an appropriate reward between changing two states. And for each state, we can define the so-called state action value function, denoted Q, that defines how from that state we can optimally reach our goal. So if you look here at the, let's say, starting state, we have here two actions, A and B, and for the transition for the next state, we can achieve two rewards. The first reward for action A is 1, the second reward for action B is 2. And if we don't know anything, then of course we will all choose action B, because that would be the optimal action for a better reward. But if we know the whole process, if we did these, let's say, decisions a few times and learned some experience, then we can write in our this state action value function Q, the whole reward from reaching the current state to the final state. And when we look here at the current value of the function Q, from state A, when we use action A, the reward is 12, because when we go in this path, we have bigger rewards after that. And here, when we choose in the beginning action B, we have here a very large punishment for this. And after that, we receive just a good reward. Like, let's say, when we go in the morning without an umbrella, and of course, when it's in the beginning a sunny day, that's a good reward because we do not have so many things with us. But if the weather is changing and we get wet, and let's say we have to perform a lecture, and we have an audience, and we came to the lecture all wet, our computer doesn't work anymore, then we have here a huge punishment. So it is good to know what is happening during the whole process. To learn all of these Q values, then we have to describe our Markov decision process, and this is done by using a 5-tuple. It is denoted here, and these 5 elements are a set of different states that can describe the process good. We have a set of actions A, and this set contains all the possible actions that we can apply on our process. Then we have a reward function that uses the current state, current applied action, and the future state to compute if that action was good or bad. And then we have a complicated part, and this is the transition function between different states applying some action. If we want to apply our actions, let's say, in an optimal way, we have to know the transition functions, how to reach the goal optimally. And this transition function is here problematic because in the beginning we don't know what are the good actions to apply. And we also have a discount factor called gamma that takes into account how much we will take the reward from, let's say, local action and how much reward we will take from long-term action. And those long-term actions are crucial when we have to apply a longer sequence of actions to reach an optimal state. So the idea then is to learn the so-called optimal policy, this transition function here, to see what is the best mapping between our various states of the process, and for each state, what is then the optimal action that has to be applied. And of course, if you look at this, then these state action pairs, these Q values, present the knowledge how we can, using those actions, optimally come to our desired goal and improve our traffic controller. For this, in many applications, the so-called Q-learning algorithm is used, and it is presented here. And as we can see, the Q-learning algorithm iteratively approximates this state action function Q, and it is usually represented as a matrix. And when he does it iteratively, that means that he uses old knowledge, or let's say its current knowledge, and he uses new information and existing information to create a difference, some new experience, some new knowledge, and with the appropriate learning rate, he includes the newly gained knowledge into the new Q value. So in this case, we have, when we look into this new information, we have our reward that we have received from the action that we have applied, and then we entered a new state as comma in this case, and of course regarding this new state there is another optimal action to reach let's say a better state, and this is let's say the future reward that can be achieved after the action that we did. And using this discount factor, we can see how much we want to use local decision or long-term decision. And if we define this Q matrix, and it is compounded from different actions and different states, and for each state we can possibly apply any of the action. To learn this Q matrix, we have to visit each state action pair at least once. And if we have a simple process, then we can do it, but usually we have complex processes, and of course many states and a larger number of possible actions. And then we can have the problem of convergency, because we have to visit every possible place at least once, and of course refine the knowledge. And this ends with a so-called curse of dimensionality, and we want to, let's say, reduce always the dimensionality of such processes, because if we want to describe a complex process very good, then for each state we have to define a larger number of so-called classes or discrete values. Regarding the Q-learning algorithm, we can go now through the steps of this algorithm, and the algorithm starts at first just by initializing its Q matrix with small random values. And this is, let's say, some baseline, some basic knowledge. And this is random knowledge, just like a little kid that doesn't know what to do in the first thing. Then the learning process is starting, and first the system observes its current state S, and then the system picks an action and applies it to the process. He waits a little bit so that the process enters into his next state, as comma, as denoted here, and he measures the current reward. And after that, he applies the Q-learning algorithm, and here is the, let's say, old knowledge is put into the brackets from the previous formula outside, so we can see here the influence of the parameter alpha, that is the learning rate. So we, if we want to put more emphasis on the current knowledge or on the new knowledge. And after we have applied our update of the Q matrix, we just repeat step 2 over and over again until we have learned everything. And regarding this learning rate alpha, that's a parameter that's defined in the range from 0 to 1, and usually it is changed during the learning process. And in the first, of course, our agent doesn't know nothing. So in the beginning, he has to learn a lot, and in the beginning, if we don't know nothing, we want to apply a larger value of this learning rate to improve convergence. During time, if we have defined everything good, we can reduce this learning rate to preserve gathered knowledge and just to refine the knowledge. Because during our learning process, we can receive some bad information, some bad example, and we don't want to allow that bad example to ruin the knowledge that we have already gathered. And of course, in the beginning, there is no knowledge available, so that doesn't make a problem. Now, regarding the part that I said that the Q-learning algorithm has to pick an action. There's a question how to pick an action. In the beginning, the agent doesn't know anything. So in the beginning, the agent picks a random action. And this is related to the so-called exploration-exploitation scheme. And exploration is meaning here that we have to go to all of the possible state action pairs to see every possible solution and then to learn what's the optimal one. So in the beginning, we have the exploration because we need to fill our Q matrix, and the agent applies only so-called random action. After we have done a few iterations of learning, we then decrease the learning rate and apply more and more the exploitation part, and that is meaning that we have some current knowledge, and for more and more states we know what is the best action, and then we can apply it to our process. And for this exploitation scheme, there exists, let's say, a number of different approaches, and in our work here we use the epsilon greedy approach, meaning that we define some probability epsilon, and we can pick the best action with this probability, or we can pick a random action with the probability 1 minus epsilon. So during the exploitation scheme, we at the first pick random action, and after that we pick more and more those optimal learned action. Some other approach that can be used is the so-called Boltzmann or Softmax approach, and using this approach we have also two possibilities, and the first one is to pick the best action according to the current Q matrix from the current state action path that we have learned, or use the Boltzmann law presented here and let's say augmented to so it can use these Q values as input, and during the learning time the temperature is changed, so we of course at the beginning pick more random action, and after that we pick more and more best actions according to the appropriate Q value. And to conclude this part of reinforcement learning, we adapted this basic principle to variable speed limit control, so we can let's say compute some optimal values of the speed limit according to the current traffic situation. And to measure the state of our controlled traffic process, we used part of a urban motorway with 4 segments. And regarding those 4 segments, in the 4th segment we had the problematic area. And to see what is the state on the urban motorway, we used here, as we can see, the density values, so the traffic density in the 3 segments. The 2 segments before the problematic one, and then the segment that is the problematic one. And the last state that we have used is this action from the previous time step, meaning the speed limit value from the previous time step. As actions, we chose different values of speed limit, and we used here 2 sets of those actions. The first step set using, let's say, a larger number of speed limit values, and the set A2 with a somewhat smaller number of the action set. Because when we look at this possible number of actions, then they define the complexity. And in this case, we used to code our density 5 different classes. So if you want to look into different possibilities regarding our states in cases of these densities, then we have to multiply 5 by 5 by 5. And only regarding densities, we have 125 possible states. And we look at these past actions. So we can see here we have, let's say, another 5 possible actions in the states, meaning that we end up with 125 multiplied by 5. That is, if I compute it correctly, 625 possible states. And of course, then we have of each of those possible states, we can choose one of those possible actions. So we have to multiply it again with 5. And in this case, we have more than 3,000 possible combinations that we want to explore. Of course, for better control, we have to increase the number of classes in our states, maybe increase the number of actions, and then we have the curse of dimensionality because our Q matrix enlarges, enlarges, and enlarges. As a discount reward parameter, gamma, we used 0.8, and that's let's say some of the recommended values regarding Q-learning. And here is now our reward function. And if we look at our urban motorway, then the thing that you want to do is to have the maximum possible speed on the mainstream. And of course, we want to have the shortest possible queue lengths at our on-ramps. And for this, we can use our measure total time spent. And this measures, as explained earlier this week, means that we measure the time that all of the vehicles are needing in the motorway network. And of course, we don't want to maximize those measures. We want to minimize. So we have this minus sign here. Of course, when we apply speed limits, we want to enlarge the speed limit value to have in every time the best, let's say the highest possible speed limit. So we give a positive reward if the speed limit is above 130 and the traffic conditions are allowing it. And we have the reward 0, that's meaning neutral, if we have, let's say, speed values on the motorway between 105 and 110. And these values were measured during our simulation to see what would be the best reward in this case. And if we look at our speed limit control, we have to look at some regulations and the driver behavior, and we don't want to make significant changes between two, let's say, consecutive speed limits. So we are penalizing if we have large changes of speed limits, so larger than 20, and we also penalize changes of speed limits between consecutive time steps, because we don't have oscillation between those speed limits during time. And now, to look into some possible approaches to solve the curse of dimensionality, we can apply so-called state approximation. And this is useful because we have many real-world problems that have continuous states. And regarding our traffic processes, we can measure the speeds, the density, the flows, and these are continuous variables. And our standard Q-learning algorithm deals with discrete states and, of course, discrete actions. And, of course, if you want to describe, as I said, those continuous states, we need many discrete states. And we saw a little bit ago the curse of dimensionality. For this, we use then state approximation to not use such a Q matrix when we have as rows different states and as columns all of the possible actions. So we have to visit every possible cell in those matrices. We can apply a general purpose function approximator. So as an input, we have our continuous states and the action that we want to apply, and as a result, this approximator gives us the appropriate Q value. The basic approach is to use something so-called linear function approximation, and this is good for large or continuous state space. And in this case, we approximate our Q matrix that uses the state action pairs with a linear combination of a parameter vector theta, and we have here the feature vector. And this parameter vector theta minimizes then the mean squared error between the action value that we have approximated and the true value that we have related to this action. And to do the update, we use the so-called stochastic gradient descent update rule, and this is basically the Q-learning concept. The Q-learning concept adapted to this linear approximation function. And if we have this parameter vector and this feature vector, then our feature vector is related to our state vector, and it has all of the imported state incorporated in this feature vector. And this is feature vector is generated as it given here, and in the first part we have a so-called baseline, a bias value, so we always have at least one feature of our state space that is active. And in our, let's say, research, we tried two different approaches for state approximation, that's style and coarse coding and radial basis function. And to apply the state approximation for the problem of variable speed limit control, we first created a, let's say, better state vector that could take into account two previous actions, that meaning the speed limit values from two previous time steps. After that, we used also, as before, the densities in our controlled sections that were 3 in that time, and we looked into the situation of our motorway using the speed value in the control section. That's not the speed limit value, but the current speed, so we can adapt better the speed limit one to apply with the corresponding current speed limit value. And before we use some classes to discretize the state space, and now we make a normalization of our state variables, and we normalize them into the interval 0 to 1 by using appropriate regarding density. We are using the jam density because that's the maximal density, maximal number of vehicles that can be on a motorway, and the maximal free flow speed, and the free flow speed is in our case equal to the maximal allowed speed, and this is the case of Croatia, 130 kilometers. And by using this state vector, all of the parameters of our state vector will be in the interval 0 to 1. So if we gain some knowledge in our simulations, we can use that knowledge and apply it on different places and different countries, because as you told me yesterday, your maximum speed limit isn't 130, but is 120. Yeah. So in this case, we have the maximal value 1 in the learned knowledge equal to any normalization value, and that's good. For our update rule, for our Q-learning algorithm, we use then the learning rate defined here, and the learning rate dependent of the parameter k, that's the so-called number of tilings, and I will explain the meaning of tilings in a minute, and n is the number of the current simulation. So during our simulations, we gradually decrease the learning rate. And for the exploration-exploitation scheme, we use the mentioned epsilon greedy algorithm, given with this function here. And of course, this epsilon value is reducing during our simulations. And when we have learned some knowledge, we don't want to stop. We want to allow our system to learn something new when there are some changes in the system. So when our epsilon value reaches 3%, then it remains constant. So when we apply, let's say, consecutive 100 actions, 3 of them will be random so that the system can explore and learn something new. As I said, we used 3 different approaches, or we checked 3 different approaches to state approximation, and the first thing that we used is so-called coarse coding. And the idea of coarse coding can be seen here, and it comes basically from the Q matrix, when we have the Q matrix presented by states as rows and action as columns. And in this case, we have the same space. So we have here the states, we have here the actions. And then we don't use cells that are not overlapping, but in the 2D case, we are using circles. And as we can see here, the circles are overlapping. And if we have observed some state that we want to solve, then in the same time, different circles or approximators are active. So we can use not only the knowledge from one cell, as like in the Q matrix, but we can use the knowledge from different approximator cells, in this case, the 2D space circles. And for this, of course, when we detect a current state, we have to create a feature vector using binary values, and only the circles that have been chosen have the value 1, so they create the final decision. To adapt this for variable speed limit control, we use then an 8-dimensional state space, because our state vector used 8 values. And because we have 8-dimensional state space, we cannot use circles. We then use 8-dimensional hyperspheres. So like a sphere, but in many dimensions. And to cover all of the state space, we placed 900 points randomly, and looked into that we have an overlapping effect between those hyperspheres. So our binary feature vector has the dimension 1 plus the cardinality of our action set and L was here the number of tilings that we use, meaning that is the number of those hyperspheres that we use to cover all of the hyperspace. And of course, each possible combinations of action on hyperspheres regions, because the states chose the hypersphere regions in this case, we have a unique component in our parameter vector Q, and this is the knowledge that we want to apply. A similar idea is with tile coding, and the tile coding has been developed from the beginning Q matrix, when we have, as we said, rows as let's say states and columns as actions. So if we have only one Q matrix, we have one tiling. But if we want to define a better description, we can shift those tilings a little bit in the X or Y direction, and then by doing this, we can cover a larger space, not only with one tiling, but with more tilings. And the shifting is done using this vector D, and we create this fundamental unit to make the dimensions of shifting in various directions. So in this 2D example, when we define or observe an appropriate state, that is here the white spot in the middle, we don't use just one cell in our Q matrix, but we use different tilings. Then each tiling contributes to the final decision, so we can have then approximation from many tilings, and we can describe again our state space better. Of course, for the application for our speed limit control, then we again use tiling in 8 dimensions, because we have 8 elements in our state vector, and then we use P on M0 spaced, in this case not 2D tiles, but again we are in an 8-dimensional space, so you have to be, let's say, a little bit imaginative. So we have, in this case, hypercube tiles. So P is 3 as a number of tiles that we used along one dimension, and M0 is, in this case, the dimension of our state vector S. And again, we need a binary feature vector, so we can detect which tilings are active, and the dimension of our binary feature vector is again 1 plus the cardinality of our action set multiplied by L. Well, L is K multiplied by P on 0.08, and K in this case is the number of tilings that we have been using. That is 64 in this case. And for us, the number of tilings of 64 was enough to achieve a good result. And at the end, here is our vector for displacement of our tiles that we have created, and we did this shifting, as we can see, by this ratio. And the weight of the shifting that we have done is given this with this equation here, and this is, let's say, a recommendation from the literature. And by using these small shifts, then in every state that we can, let's say, observe, we have then K overlapping tiles to do the approximation. And as the last method that we have looked into, we use so-called radial basis function. And in this approach is to make a generalization of the coarse coding by using our feature vector, in this case not to be a binary one, so just to choose the number of tiles or those hyperspheres that you want to use for the final decision, but we use the Gaussian response. So in this case, our feature vector is in the part from 0 to 1. And of course, regarding our, let's say, radial basis functions, we can use different functions according to the process that we want to control. And in this case, we use it, as I said, Gaussian functions in it. To apply this for variable speed limit and control, we of course have to define our parameters, and the dimension of our feature vector is again depending of the cardinality or of the number of possible actions that we want to apply, and of course of the number of tilings or the number of these Gaussian functions that we want to use, and we have to define this value sigma. It is meaning what is the weight of those Gaussian functions we want to use in our final decision, and those Gaussian that we have defined were again randomly placed within our state space and overlapped so that not only one Gaussian function is affecting the decision, but more Gaussian functions are used. And it is now important to emphasize that in all of the mentioned approaches for state approximation, meaning coarse tile coding and radial basis function, the component in our feature vector that is associated with action, and if some actions are not executed in time t, because we will execute only one action, all of the other values will be 0, except for the beginning bias term, so that we can ensure that always at least one action will be executed. And now, when we have this explained a little bit how we can use those state approximation, we can do a simulation of this traffic process. And for this, we again used our macroscopic simulator vSim. And in MATLAB, we implemented our controller so that during execution, we have a closed loop, and vSim simulates the traffic and also the needed measurements. And in MATLAB, the computations are done, and the computed speed limits are then sent to vSim, and then he acts them up on the urban network that we have simulated. Here you can see our segment of the motorway that we have used. It has, as mentioned before, 1, 2, 3, 4 sections, and the densities and velocity that I have been mentioning before are related to those sections here. Regarding the, let's say, traffic flow, we have a constant mainline flow here, and the flow on the on-ramp R2 is changing as it presented by this, and in some time frame we create congestion here at this bottleneck area, and of course this congestion spills upstream in the other direction of the moving vehicles. To control this motorway, we applied variable speed limit control, and the green area was under the speed limit. And of course, we simulated here a variable message sign to post all of the speed limits on the motorway. And new speed limits were computed every 300 seconds, meaning every 5 minutes, and new traffic data were collected every 30 seconds. And to look into the behavior of different approaches to state approximation when we do reinforcement learning, we did first a normalization of the achieved TTS, because as you have seen before, these processes are random. We randomly choose the actions in the beginning. And if we choose something random, then we will obtain different values of this measure total time spent that we used. So the normalized value for all of them in the beginning was 1. And we can see here that our classic Q-learning algorithm that uses full state representation, or our Q matrix, has the ability to learn something. He reduces this total time spent measure that is in his reward function. But as we can see here, the convergence isn't pretty fast. So we want to do something better. And this is the motivation why we looked into this state approximation in this case. As we can see here, all other approaches that we use for state approximation have a faster convergence. And this is something that we want to do. And at the end, if we look the final value that the system achieved during learning, we can see here that this black line that's belonging to course coding achieved the smallest value of the total time spent. So it reduced the beginning value of the measure total time spent for about 10%. But we have to be careful here. In this case, that this isn't meaning that we have improved our, let's say, level of service on the motorway compared to the no control case for 10%. That isn't true, because we are starting with some random actions. And random actions can, let's say, degrade the level of service. And this is something that can be best seen here. As we said, in the beginning, only random actions are being applied because we are in the exploration process. The agent doesn't know anything. It's a small kid just trying to do something with its environment. And this is the red characteristic here. So we have many oscillations and many changes and significant changes of the speed limit. And this is not good when we control a motorway. The good thing that with time the agent can learn, and we can see here the green characteristic, and this is after something about 1,000 simulations. So we can see here that our reward function penalized such big changes in the speed limit, and also penalized the oscillations between consecutive speed limit values. So we can see here that this green one has smaller changes and smaller number of oscillations. But of course, this is not good yet. So if you do a little bit of more simulations, and we did for every case about 5,000 simulations to learn this thing, after a sufficient number of simulations, we can see here that the algorithm has learned to gradually decrease the speed limit, then hold its value as high as possible, and after that, of course, decrease the speed limit to achieve optimal behavior. And looking into the traffic parameters in segments, in this case 3 and 4, so 4 was the problematic one in our model, and the segment 3 was before the problematic one, we can see that the controller was able to rise the average speed of traffic during congestion. So this is the behavior, the black one, without applying this traffic controller. Regarding density, on the problematic area, we have a somewhat lower density, so we're not so close or over the critical one. And regarding the traffic flow, in some areas we have increased traffic flow, and because the congestion dissolves earlier, then we can see this in this part of our diagram in section 4, where the flow is somewhat lower. If you want to see some more details with a more detailed analysis on some other traffic parameters, you can look here into this paper that I did with my PhD student Krešimir Kušić, and this paper is available on my web page, or you can download it from the IEEE Explore database. And to continue, I can show you just briefly also an application that we did to ramp metering, and this was, let's say, a rather simple one, and this was done, let's say, as the first one when we started looking into some possibilities to do some online learning during operation. So in this case, we used for states our phases of our traffic light, and for this we use the green phase that lasts constantly 3 seconds in ramp metering. We use the all red phase, and in one implementation we could also switch the ramp metering off, because we wanted to look into the behavior when we had significant changes of traffic demand. We also used here the density on the motorway, and we used 3 classes as denoted here from 0 to 2, and we used the cumulative number of vehicles in all lanes per kilometer. So as you can see, these numbers are pretty big in this case, but as I said, they're using the numbers of all lanes combined together. And we also looked at the queue length on our on-ramp, and we wanted to minimize that queue length. So we looked into 2 types, and the first type used then 3 phases, and the second type 2 phases. So one could turn the ramp metering off. The actions were very simple. We could switch the phase or stay in the current phase, and regarding the reward, we added some reward when the on-ramp queue and density were low, and for other values we added a punishment. And here you can see our simple simulation model. So that's a part of a motorway consisting of a mainstream and of course just one on-ramp, and on the on-ramp we measured the queue length, and on the mainstream we measured the density, we measured flow, and we measured of course the speed. For implementation, we again used vSim connected with a C# application and a database to store the queue matrices that we have used during execution. Here you can see the traffic demand that has been used in this research. So the blue one, that's a characteristic on the mainstream, and the red one was the flow entering on the on-ramp. As you can see here, this is, let's say, classical situation. During nighttime, we don't have, let's say, any traffic almost at all, just a few guys returning from their night shift or from a party. And in the morning, we have the morning rush hour, then the demand falls, and then we have the afternoon rush hour, and then everything, of course, goes back to a low traffic demand. If you look at the results, we use the case without ramp metering as, let's say, a baseline to see what will happen. And in this case, when we applied Q-learning, and this column here is related to the option that the ramp metering is always on, also in the case of a low traffic demand. So we can see here that with such an approach we can cause problems. Because of course during the night time, when there is low traffic, we don't want to stop our vehicles on an on-ramp. But when we use the second type that had the possibility to turn ramp metering off and on. Then the system recognized, because he received punishment here for his bad behavior when the ramp metering has been off, then he learned to turn ramp metering off, in this case here, and turn it on when we had high traffic demand. And in this case, we can see that we can improve the situation of our on our urban motorway. And we can then learn when to use, let's say, a traffic controller and how to use it best. So when we look into the achieved speed and density, then by applying ramp metering, we can increase the speed on the mainstream, and we can decrease the density on the mainstream. But on this other diagram here, we want to look the case when ramp metering was always off. We can create problems because when there's low traffic demand, we are stopping the vehicles, and we can create some beginning queues when high traffic demand has coming. And because congestion needs a lot of time to dissolve, we can cause problems that are lasting during the whole day, and then we have poor behavior. And if you are more interested in reading about the system and achieved results, everything is published in these two papers here, and of course they are freely available on my personal webpage, so you can download them and read me and contact me for some details. And to come to my to the end of my today's lecture, we can summarize what we have seen here today, and we can conclude, okay, that if we use some learning from artificial intelligence, we can improve our traffic control algorithm during operations. And there are some systems in this world currently that are being testing using this. But before we can use this system in a real-world application, we have to learn some basic knowledge using simulations and, of course, calibrated models, because in the beginning the agent uses some random action that can cause problems. And we don't want to apply random actions in, let's say, in dangerous situations. That's not good. The convergence can be problematic, and for this we have to use appropriate statist representation and, of course, approximation approaches to improve our convergence rate. The reward function is very crucial, and we have to design it carefully so we can include restrictions regarding traffic control. And this is now, let's say, the main issue when such systems are applied in traffic control. And last month there was a guy from PTV, and he presented some, let's say, research that they are doing in that company. And of course PTV, just in case, is the producer of the simulator VSIM. And then they also want to make a new system that can learn during operation, because their current system are adaptive but and use some optimization but are not learning during operation. And they did some implementation, and they have now the problem when regarding signal programs, the phase length is changed very significantly, and the phase order sequence is changed without, let's say, taking care of a natural crossing of an intersection. So the system gets optimal results, that's okay, but it isn't good for humans, because we cannot live in such a world. When we know something, then we'll use it, and then we can cause problems. And as the end, now there are new concepts of so-called deep learning and deep reinforcement learning. And the good thing about these systems is that they can use information about every vehicle. And this is very interesting today when we have the development of connected and autonomous vehicles. So the system can take into account current speed and position, in this case of every vehicle, having the option to do a microscopic measurement of the current traffic flow, traffic density, traffic speed state. We are currently working on it, but the system isn't stable yet, so I am not able to give you some results, but just to mention that such things exist and people are working on it. And this would be the end of my today's lecture to you, and I can say to you, hvala, obrigado, thank you for listening, and if you have any questions, do not hesitate to ask me.
So thank you, Professor Eduardo, and thank you everybody that are watching us, even on YouTube, and the people in São Paulo campus. And we are trying to connect them to our questions for both campus. And here in São Carlos, anyone have any question? Do you have any question? Yeah. Professor Marty, vocês estão nos ouvindo aí?
Hey, hello. On your slide number 20, yeah, okay. I think it's 20, yeah. You said that you apply a learning rate that decreases over time, right? Do we function like that, humans? Because doesn't that make us make the system stubborn, like the system knows something and it's like kind of like refusing to learn new stuff?
Okay, very good question. And for this we have to look firstly in our human behavior. So when we are small kids, babies, the only thing that we know is to cry, to take some food, and to poop. And then we repeat those things over and over again. And gradually we start learning something. And in the beginning, our brains are empty and our neurons are connecting themselves, and we'll learn very fast and very huge amounts of things. So when you are learning a kid, if you miss some time frames to learn the kid how to walk, how to speak, etc., it will not be able to learn that later again. So we had some cases when kids were left to in some places and animals rose those kids and they are behaving like animals, and you cannot teach them anything more else. So yes, this leads then that you mentioned stubbornness, but if we watch in this case that we are controlling only one process, and to control such a process we need some basic knowledge, and this is the most important thing to learn in the beginning. So in the beginning we are learning the basic concepts how a process is behaving, so this is then the larger value of the learning rate to improve the conversions and to gather the new knowledge. After we have grasped the basic concept how the process is functioning, then you only need to see how is it functioning in, let's say, some special cases to refine our knowledge. And in that case, we don't want to destroy our basic knowledge. Then for that case, we then using then this smaller number, the let's say smaller learning rate. But to ensure some mechanism that our system will not be stubborn all the way, we using, let's say, these peak action algorithms, we leave a possibility so that the system will apply some random action every certain amount of time, and then we can gather that new knowledge. And of course, when we pick random actions, then we can have very bad behavior. We don't want that such a bad example influences our basic knowledge. Yes.
More questions? No? People from São Paulo, are you listeners?
Yes.
Yeah. Do you have any questions? Yeah, we are listening.
Yes.
Do you have any
Listen.
questions?
I believe not. I believe not.
Será que ele está escutando?
Can you listen, André? Can you listen?
Yeah,
Yes,
we are listening.
hearing you.
No question here.
You
No
don't-
question here. Okay.
Don't have a question, so let me try one here. Yeah, you said about the Q matrix. Of course, you manage your system, and you could increase and make it more complex, the agent theory. But you decided to put in your system only 2 segments before and the critical segment. But have you tried another configuration of that? And how long was the segment that you have tried?
Okay, here we can see the model, and regarding the whole length of the segment, that was, if I calculated correctly, about 4.5 kilometers. So if you look into the length of the segments, etc., then you have to take into account the driver behavior and of course something about the traffic flows. So we noticed that with the settings of for motorways in WISIM, that a longer segment is preferred to be under speed limit control, that the vehicle could decelerate. Because if here we have this variable message sign and the speed limit starts here, that doesn't mean that the vehicle are here driving with the speed limit. So they have a small distance here, a few hundred meters, where they don't react at all. So after that, they are decreasing its speed, and then they achieve the speed limit. And then after that, we can ensure that the speed limit is obeyed when they enter the congested area. So regarding these lengths, there is a many of research how to place, let's say, the message sign, what distance before the congested area. And the latest work of Markos Papageorgiou proposed that the speed limit area should end before the congested area, so that the vehicles start a little bit accelerating into the let's say congested area, because if there is no traffic, then the vehicles from the on-ramp will have similar speeds to the one on the mainstream, because both of them are accelerating. And if the case there is a congestion, then the people leaving the speed limit area will see that there is a problem and will not accelerate at all. Maybe that everybody can hear you.
Did you consider to use different kinds of reinforcement learning algorithms or different models of artificial neural networks?
Well, to come to my summary, we used for now this classical Q-learning, and that was done in a master thesis of one of my students. And then we saw the convergence problem, and then we looked into different state representation to improve the convergence problem, and this is that what has been presented here. And currently we are looking into this deep reinforcement learning to use for the state representation deep convolutional network, and the input to that network are not the measured states like density, speed, flow, but we using current speed on position of every vehicle. In WISIM you can gather all of this information from every vehicle. It lasts a little bit, but you can obtain it. And also, if you have an environment of connected vehicles, then you can assume that you can gather all of the speeds and all of the position. The GPS measures them. Bless you. And we are using this as input to our convolutional network that learns the Q function, the state action approximation. So this is being done, and one of our computers is using those GPUs to learn something. and now we have the problem that our convergence rate and our reward function isn't, let's say, quite yet refined, so we're having some problems here. So we are trying to solve this now. So yes, we are using other systems, but I cannot show you anything regarding the results yet. Maybe next year or next time.
Hi, Professor. If some accident occur in the region of the controller, we should turn it off, or does it understands that it's an unusual situation?
Mm-hmm. Yes, this is a very good question. Just let me go to one of my basic slides when I have mentioned yes. So the idea is to learn some optimal policy between those state action pairs. So when we're learning such policy, we can use an agent to learn only one policy. And in this case, we learned only one policy to improve the traffic situation on an urban motorway. Okay? But if you want to include other, let's say, other situations, and let's say in the urban environment, you have, let's say, preemptive control for priority of emergency vehicles, you have possibly incident, you have special situation if there's a concert, a match, if there is a politician or a VIP person traveling to the city. So for all of these situations, you can use the agent and learn another policy. So your agent has not only one policy, one control law, but different policies, different control laws for these situations. And in that case, you can use an operator to switch between those policies, or you can use your processing of the measured states to see from your historical data that you can, let's say, recognize this incident situation or politician coming or preemptive control, whatever, and then in your agent you switch between those policies. And then you can apply, as you said, that learned knowledge in the same framework. So using the same inputs, the same outputs, but you are just using a different way to do something. So it is possible, yes.
More question? In São Paulo, anyone? Anyone?
Eu tenho uma dúvida. Is it possible to use this kind of simulation in more complex junctions? Can you hear me?
Yeah.
Yes, just to repeat the question, so you're asking if the simulations are possible in more complex environments?
In more complex junctions.
Ah,
if you
yes.
have, for example,
Yes.
more than one movement.
Yes, okay. So this was just an example of an urban motorway and also with on-ramp metering. These controllers can be also used on intersections. And regarding one intersection, you can have all of the, let's say, possible phases with all of the vehicle movements on it. If you just, let's say, have a bigger number of states of your intersections that you want to detect, and of course you have a increased number of actions that you want to apply. So if you want to look about, let's say, more complex applications of this approach, I can recommend the papers from the Professor Ivana Dusparic from the Trinity College of Dublin, and she looked into how to apply such agents into an urban environment controlling different intersections. So not just one, but several intersections that are heterogeneous, meaning that they have different configurations. And they also applied different policies to solve the problem of priority preemptive control of public vehicles. The current drawback that is existing now with her work is that the phase length and the phase sequence is not complying, let's say, as an example, with a NEMA structure. So the system changes the phase duration and the phase sequence as he thinks it is optimally. And if you learn some behavior on an intersection and you as a driver come to that intersection, then you use your knowledge and this can cause problems. And we have now applied for a project, and if we get the funding, maybe we can work on solving that issues.
Thank you.
In São Paulo, thank you for a great presentation. I have a question. In your presentation, you said that you used micro simulation data, and I want to ask if possible to use real-time data from crowdsourcing like Waze or Google Maps traffic data. If you think that this kind of data is effective to improve the speed control that you proposed.
Okay, thank you for your question. So just to repeat, if I understand everything correctly, you are asking if I can use some other sources of data like Google Maps,
yes.
etc. Okay.
Waze is the
Real
GPS data.
Okay, so just these data are available in real time or just historical ones?
Well, both.
Okay, so when we look at the basics of control, this is the block scheme here. Then every control system, if you want to control something in a good way optimally, then it has to work in real time. So you have to have access to some real-time measurement to act locally and to solve your problem. And if you're doing some control on a bigger level, so let's say from a traffic control center like you, then you have to take into account the whole situation. So in this case, when we see our, let's say, urban traffic network, you can detect in some data like Google Maps, some areas that are beginning to become more congested. So in this case, you as an operator can, let's say, switch policies on some controllers so that they are acting in a different way. So then you're using something that's so-called hierarchical control. So you have on the low level all of the controllers that are using your real-time data to solve locally the problem. And on the upper level, you are seeing the whole picture here, the whole network, and then you can decide what to do with your controllers. And let's say such historical data are very useful in such control approaches because, as we know, traffic behaves similar in similar days. So if we have a normal working week, the traffic on Mondays will be, let's say, the same, on Sundays, etc. And you can use then settings to accommodate for these changes, and then use those local controllers to react to to some measured changes that are not in those upper level data. So it is possible in some way.
Okay, thank you.
Professor Edouard, when asking my first question about intersections, you told me to see articles from another teacher. Can
Yes.
you repeat the name, please, slowly, please?
Well, that's no problem. We have in my program a visit on Monday to your university, and I will have also another lecture there. I believe you are free on Monday.
Well, after my test, I'll be free.
Okay,
After the test.
After the test, I'll be free.
Okay.
Probably late.
Okay.
But we could send to you the article, the paper.
Yes,
or to the Professor Marty or Leopoldo.
Yes.
Oh, thank you.
Since I will be on Monday.
The name is not easy for us, but
Yes, I'll be there on Mondays, and I can, let's say, give you a set of my papers and the papers from the mentioned professors, so you can look at them, and then, if needed, you can contact them. So I believe Professor André knows your name and contact, so I can give it to you. And if you are able to grasp it, because it's a Slavic name. That's a Trinity College from Dublin, from the statistics School of Computing, and her name is Ivana Dusparic. Ivana Dusparic. I will send it with an email.
Better to send to you.
Yeah.
Ivana, it's easy to understand.
Okay.
Thank you.
More questions? No?
Can I make
Yeah.
one? I
Yeah.
am wondering, thank you for your presentation, Professor. It was very interesting. I was wondering, the most important issue there is that you need to estimate the Q matrix in every iteration, right? I was wondering if you can estimate some parts of the matrix that are more likely to be chosen instead of others. I mean, if you need to populate the whole matrix in every iteration, or if you can choose just parts of it.
Yes, thank you for your question. Just to go to the slide that represents our Q matrix. So when we
Sorry, we can't see the screen because it's quite a
Hey, we need to have
white.
a contrast.
The contrast is not good. But
okay, the technician will solve it now, and then I can answer the question.
yeah, maybe if you turn the camera, please. I don't know if it's possible. If not, just
this
let us know.
camera there.
Melhorou. Tá melhorando, acho que...
Yeah, that's fine. That's
Okay.
great.
Okay, good. Now
Right.
use your photographic memory if it's needed.
Yeah.
Okay.
Yeah.
Good. I will stand so not to cover the figures. So when we define the states and the actions, we have to create the whole Q matrix. And to grasp fully the behavior of our system, to learn how to control it, we have to learn something for every cell for that Q matrix. And when we do one iteration of learning, then we in this case then we estimate just one state, and we let's say then iteratively learn only about one cell. And in this case, we need many iterations. So that you mentioned using different part of those metrics, there are some approaches for complex system when they look which part of the matrix, which states and actions are used more, and they are concentrating more on that part, because maybe some combinations of state and actions will never appear. And this is then the case that we have a low convergence rate, and to prove this we use then those approximators, because if we grasp one state action pair, it affects not only one cell in the Q matrix, but affects a whole hypercube or a whole hypersphere in the state action space, so we can learn it more faster. And yes, such approaches that you asked exist, and the thing is that in the Q matrix we in each learning iteration we do not go to the whole matrix, but just one cell according to the current state action pair, and then you have to look that you cover all of those during your learning period. And in this case you want to cover most of them, and know that you will have a generalization approximation of some states that have not been visited and have some basic knowledge. So that's better then.
All right. Thank you very much. Thank you for the efforts. Thank you.
So, thank you everyone, especially who are watching us on YouTube. And thank you, Professor Marty, for everybody, Professor Leopoldo, Cassiano. Just to remember, on Monday, we will have one lecture in Escola Politécnica in São Paulo. The time is 10:30, if I'm right. And we will be there in São Paulo and then transmit to São Carlos. So thank you very much, Professor Edouard, for all your lectures during this week here. And now we have a trip to São Paulo, and we will see and meet the big city in our country. And thank you here, everyone that come.
André?
Yeah?
Excuse me. Please, Edouard, can you
Yes.
have a brief your presentation
Monday?
in Monday?
Yeah, the name.
Can you
Yes.
take us a brief?
Okay. So first, I'm looking forward to see you all on Monday. And on Monday, I will talk about cooperative systems that we can use for traffic control. And it's basically a presentation from a PhD defense from my doctoral students. And in that thesis, I will cover the concept of cooperative control that we can use. And I will describe our system at Integra that we have used to learn cooperative control, meaning that we have combined ramp metering on several on-ramps using an ANFIS neural network, so we can grasp the best possible behavior using all of the possible results from classic algorithms. And I will then present some results that we achieved using a macroscopic simulator in MATLAB.
The macroscopic simulation is from PTV?
The macroscopic simulation is from a simulator called CTM Sim, and it's a simulator produced by MIT in the States. They use that simulator to control, to check their controllers on their highways, to make the computations a little bit faster.
Okay, thank you.
So thank you, everyone, and see you on Monday.
Thank you.
Obrigado.
Have a nice weekend.
Ok.
Ok.
Tudo bem.
Bye bye.
Mentira. Tudo bem.